Hello, everyone. Welcome back to this webinar on ONNX. And this is the MI2 webinar series that I run once in a month. Before I go any further, let me make sure you're able to listen to my audio and able to see my screen. So I'm going to bring up a very quick poll just to make sure that the AV experience is good. So please let me know by clicking on one of the radio buttons. Excellent. Looks like the AV is just fine. So if you are attending the webinar series for the first time, let me set the context. So MI2 stands for Machine Intelligence and Modern Infrastructure. So machine intelligence is the combination of IoT, machine learning, AI, cognitive services, and so on, while modern infrastructure is predominantly driven by Kubernetes, microservices, service mesh, serverless computing, edge computing, and so on. Now, we are at a very interesting phase where we are seeing the convergence of machine intelligence and modern infrastructure. So every month, I bring one of the sessions from these two tracks, either on the AI side under the machine intelligence or on the Kubernetes side, which is under modern infrastructure. Now, every webinar is complemented by a tutorial, code snippets, and the recorded video. Most of my content goes to the new stack. So this month I'm running a series on ONNX at the new stack. So I'm going to leave a link that you can actually follow to get access to all the resources, all the code snippets, and the discussion that we have in today's webinar. This is a completely independent forum where I bring exploratory emerging technologies from these two domains, machine intelligence and modern infrastructure. So today we have a very interesting topic, and that is the Open Neural Network Exchange. So I have multiple things lined up, but I'm going to start off with the challenges with current deep learning environment and deep learning domain, and why we need to look at ONNX as the answer to these challenges. Then we'll take a closer look at the ONNX runtime. And then I have 3 demos, which will help you understand the concepts related to both ONNX and the ONNX runtime. ONNX is also very prominent at the edge, but obviously that is out of the scope. I'm going to cover ONNX at edge in a dedicated session where I will talk to you about running ONNX on devices like Jetson Nano, Raspberry Pi, and Intel Movidius, the neural compute stick, and so on. But that's a different session. But today, this is an overview of ONNX with a very detailed discussion around the environment and the promises offered by both ONNX and the ONNX runtime. So this assumes you are familiar with machine learning and deep learning in general. You don't need to be experts, but having the background would certainly help. So what are the challenges with current deep learning? Well, if you have been tracking this space, and if you are an AI enthusiast or even a budding ML engineer, you know that machine learning and deep learning are very complex domains. Apart from learning a language like Python or R and investing in a framework like TensorFlow or PyTorch, there are many things that you need to learn. But the biggest challenge is to deal with the fragmentation and extremely distributed set of tools and frameworks, runtime, and so on. Today, when you want to really get started with deep learning, you have to deal with a lot of frameworks, and each of these frameworks are optimized and aligned with certain use cases. For example, TensorFlow is gaining a lot of popularity, and it is available in the public cloud, at the edge, even inside a browser, microcontrollers, and so on. PyTorch is very powerful when it comes to computer vision AI. Keras is now becoming the de facto for dealing with TensorFlow. Microsoft Cognitive Toolkit, Apache MXNet, Gluon, Chainer, Baidu's Paddle. We have a variety of frameworks that deal with deep learning. You can use any of these to essentially train a model, but unfortunately, there is no interoperability. For example, if you have spent a lot of time and a lot of hard work in training a model with PyTorch. Using that in TensorFlow is not very straightforward. So these languages, or not exactly languages, but the frameworks are very similar to the computer programming languages that we dealt with before JVM and Common Language Runtime have shown up. There was no interoperability between BASIC, Pascal, COBOL, and those languages. And then eventually we had JVM and Common Language Runtime from Microsoft, which made it possible for languages to share their binaries and share the libraries. But we haven't reached that point with deep learning. You have to deal with a very fragmented set of frameworks and toolkits. If that is the scenario with training, when it actually comes to the hardware and the runtime and the drivers that you're going to use, NVIDIA is the leader in GPUs, and GPUs accelerate training. So obviously, if you are dealing with a large data set and you're training a convolutional neural network, you need to have a very powerful infrastructure based on GPUs. And the moment you deal with NVIDIA GPUs, you have NVIDIA CUDA, the Compute Unified Device Architecture, and then cuDNN. Those are the layers that interface with the underlying GPU, and your high-level frameworks like TensorFlow or PyTorch will eventually deal with that. So you have to set up an environment, not just the hardware, but also the right software. For example, in case of NVIDIA, it is about CUDA and cuDNN. Similarly, Intel has FPGAs. FPGAs are field programmable gate arrays, and these are custom-made application-specific integrated circuits that accelerate training. And again, when you're dealing with Intel's FPGA, you have to use one API or MKLDNN, now which is actually called as OneDNN, the deep neural network toolkit, exclusively from Intel. And that API and that software layer interfacing with the underlying FPGA is very, very different. So you have to understand how this functions, and you have to interface with the hardware and software layers. And if you're dealing with Google Cloud, you have the Cloud TPU, Tensor Processing Unit, and that is exposed via the TensorFlow toolkit. This is proprietary. This cannot be installed in your enterprise data center, unlike an Intel FPGA or NVIDIA GPU. Google has abstracted a lot of software libraries and drivers in Google Compute Engine instances and GKE clusters. So you don't need to deal with that, but you still need to interface with the underlying cloud TPU, the tensor processing unit from TensorFlow. Obviously, it is very tightly coupled. If you want to make use of TPUs, you have to use TensorFlow on Google Cloud. But that's on the training side. So let's assume you picked one of the frameworks like TensorFlow or PyTorch or Caffe, and you have trained your model using one of these AI accelerators, the training accelerators, and an appropriate software stack. Then to productionize and to deploy the deep learning model, you need to choose the target environment. And there we have a very diverse set of environments that are available. The model that you train in the public cloud or in your enterprise data center is not directly optimized. It cannot really deliver the low latency, high accuracy, high precision throughput when you actually use it for inference. For that, you need to take your fully trained model that is coming out of one of these layers and optimize it to make sure that it is targeting appropriate environment. For example, what you see here is an NVIDIA T4 GPU. T4 GPUs are typically used for inferencing, that is running the model in production for predicting unknown, unseen data points. So you take the model and then you optimize that for TensorRT, and it goes through a process which is called quantization, where slightly higher bitrate data types are converted into lower bitrate, like converting FP32 into int8, which will lose a little bit of precision, but increases the speed of inference and also gives you better almost the same level of accuracy. So the story doesn't end just by training the model. It continues with optimization, quantization, and targeting an appropriate environment. So NVIDIA T4 is one of the popular choices. Then, of course, CPUs. Even for CPU, when you're performing inference on CPU, you still need to quantize and optimize your model. And for that, Intel has an open source project called OpenVINO Toolkit. And this OpenVINO Toolkit takes your TensorFlow, Caffe2, PyTorch models and optimizes that for CPU. And again, you have to go through a pipeline of converting your model to one of these Intel CPUs. To target edge scenarios where you're deploying in industrial automation and AIoT use cases, you need to apply a different framework and a toolkit. For example, NVIDIA has the Jetson family of products, which comes in the form of Jetson Nano, Jetson Xavier, Jetson TX1 and TX2, and so on. They don't really run an Intel CPU. They actually come with an ARM processor and a custom-made software that runs the entire stack, which is called Jetpack. So you have to now take your fully trained model and optimize it for Jetpack running in one of the NVIDIA devices at the edge. Similarly, Intel has invested in a chip, an ASIC, that is highly optimized for vision computing. That's why it is called VPU, which is Vision Processing Unit. And this Vision Processing Unit is actually a Miride X VPU and available through Movidius chip. Now, the collection of such VPUs are available in what is called as Intel's Mustang board, which is a cluster or rather a collection of such Movidius and Miride X VPUs. And again, to target this for very high throughput and low latency inference, you still need to go through OpenVINO. And finally, Google has what is called as edge TPU, which is the counterpart of the cloud TPU, but typically runs at the edge in a highly constrained, in a very different environment. And for that, you need to actually optimize your model for TensorFlow Lite. And this TensorFlow Lite is not the usual TensorFlow Lite that you target for TensorFlow.js, which is running inside the browser, but it has to go through another level of optimization to target the edge TPU running inside these edge dev boards, which are actually called as the Corel Dev Kit. You can also take that edge TPU module and use it in production in a very smaller form factor. This is just a glimpse of what needs to be done. There are other GPUs. For example, Qualcomm has a GPU called Adrion, and to target that, you need to use Qualcomm's neural processing SDK. And similarly, Android, if you want to target Android mobile phone, you need to use Android's neural network API. And similarly, iOS and Apple uses Core ML. Now, unfortunately, none of the models that you are training will be able to directly run. Even if they run, they don't take advantage. So you have to optimize it for each of these scenarios. So as you can notice, first of all, you have to deal with a very diverse, very fragmented, very, very different set of toolkits and frameworks. Then you have to deal with a very different set of training environments, whether it is in the cloud or the enterprise data center. Then to productionize the AI models, you need to choose the right hardware and the right software stack and further optimize your model that is fully trained and then use it for inferencing in production. And all of this is pretty complex, and this is not a one-time job. Every time the model deteriorates in terms of its accuracy, you have to go back and retrain the model every time there's a drift, and you have to basically build a pipeline that takes care of this entire closed loop mechanism of detecting the drift, retraining the model, optimizing the model, deploying the model, and scaling it. It's a pretty complex pipeline. So where exactly are we with this? Well, this is how you actually visualize, right? So on one side, you have all the frameworks, and on the other side, you have all the hardware environments. So the only choice we have today which is becoming very popular and gaining a lot of attention of the industry, is ONNX. So ONNX is the Open Neural Network Exchange. Think of that as the intermediary, the mediator, the coordinator between a variety of frameworks and a variety of target environments. It promotes interoperability, it promotes portability, it promotes efficiency and optimization by reducing a lot of these moving parts, by minimizing the number of moving parts you have to deal with when you're training, optimizing, and deploying deep learning models. Not just deep learning models, even classical machine learning that uses linear regression, logistic regression, and so on. So it is not just to do with deep learning, but even traditional classical ML. So that is Open Neural Network Exchange. And this was started sometime in 2017. 3 companies got together. AWS, Microsoft, and Facebook were the founding members of ONNX. So in September 2017, they got together and defined the original spec for ONNX. And the original spec of ONNX basically helped them define 2 things, which I'm going to talk to you about. One is the file format for dealing with the deep learning models. And the second thing is the actual set of operators and the graph that goes inside the file. Now, as you can imagine, when you are training a TensorFlow model and you are using the saved model mechanism, you get a protobuf file, which is a .pb. If you are dealing with, let's say, PyTorch, you end up creating a .pt file. And for scikit-learn, it is typically a pickle or a joblib file. And Cafe has its own Cafe format. Now, using one of those formats in the target environment is not possible. For example, you cannot parse, you cannot comprehend the PyTorch model in TensorFlow and perform transfer learning, or mix and match certain models to actually use it from one single language and go live for inferencing. You cannot do any of that. ONNX brings that level of portability by enabling you to export the fully trained model and importing that in a different framework. And the second component of ONNX, which I'm going to discuss, will also helps you in targeting diverse hardware environments without you doing the manual optimization or conversion. So what started with 3 companies has grown significantly. So today there are a lot of companies, the who's who of the industry from the deep learning market are now contributing, and they are associated with ONNX. So, from NVIDIA to Intel to IBM to Qualcomm, and in some of the other platforms like Huawei, Baidu, all of them are now a part of the ONNX ecosystem. They contribute and they are promoting this actively within their public cloud platforms, toolkits, and runtimes, and so on. So what were the original design guidelines and promises of ONNX? So initially, ONNX was built for the deep neural network. As I mentioned, it is essentially to export and import the deep learning models from one framework to another, but it also supports traditional ML. And as we know, this field is rapidly advancing. TensorFlow is now in 2.2, and it has gone through a significant shift from using from moving to eager execution, and also by making Keras as the default front end for TensorFlow backend. So that's just one example. And similarly, PyTorch has gone through a lot of iterations to make it more simpler and more productive and more efficient. So there are a lot of moving parts and a lot of advancements happening with each of these frameworks and toolkits. And ONNX is keeping up with that, making sure that it is supporting these enhancements and advancements coming from the framework owners. It is compact and cross-platform in a lot of ways. ONNX is to deep learning what common language runtime has been to programming languages. So I come from Microsoft. I spent about 11 years at Microsoft, and I was an evangelist for Common Language Runtime and .NET Runtime. And I vividly remember how I articulated the benefits of Common Language Runtime to my customers and how I drove the adoption of .NET. The promise was very simple. You write the code in any language, but ultimately it gets converted into one format, which was actually called as the intermediate language in the CLR context. And once your code gets converted into IL, that can be consumed by any other language that understands Common Language Runtime and adheres to what was called as CLI, the Common Language Interface. And of course, Java also pioneered something very similar. Java bytecode was a common format, and JVM was the runtime, and Java was the top level language. But eventually, other things like Scala and many languages were built on top of JVM, and same was the case with CLR. So ONNX is highly inspired by those portable runtimes and environments, and it offers something very similar to what JVM and CLR delivered to developers. Basically, irrespective of the framework and toolkit that you're using, you will end up generating a very common intermediate representation, which is called IR, that is independent of any language, any framework, any toolkit. So that gives you a level of abstraction and decoupling from the higher level toolkits like TensorFlow and PyTorch. And to make that happen, it is basically standardizing all the syntaxes, semantics, and the conventions used in the deep learning domain. So it is not a black box. It is definitely not a opaque binary that you really don't know the composition and the structure. This is extremely transparent, well documented, well defined, and very, very transparent. So that is what ONNX is all about. It's a very transparent, portable file format to basically export models written or trained in one framework and toolkit into another. So in 2019, ONNX was donated to Linux Foundation under the umbrella brand, which is the LFAI. It's a dedicated foundation, just like CNCF is for Kubernetes and microservices and cloud native. LFAI is the Linux Foundation's charter to drive interoperability, transparency, and openness for AI-related projects. Now, ONNX is a part of LFAI. So there are two things. ONNX is originally developed for deep learning, but it doesn't stop with that. ONNX ML is an extension of ONNX to support traditional classical machine learning. So when you think of an ONNX spec, there are two flavors. One is the deep learning, the artificial neural networks and deep learning neural networks, deep neural networks. And then we have the traditional ONNX ML to support things like scikit-learn. So that's about the ONNX spec. Now, when you actually export a model into ONNX, what happens is you get a model file, obviously, and this model file is it's basically a graph. And if you have ever seen the neural network architecture of ImageNet, LXNet, MobileNet, and Inception, SqueezeNet, DarkNet, TinyYOLO, VGG, you are actually familiar with the entire graph of your convolutional neural network. Now, ONNX basically can be visualized and can be explained in terms of a similar graph structure. So a model is a container, it's a logical boundary for a graph that basically represents an entire model. Now, the graph is a collection of multiple computation nodes. Now, each node is, it's exactly like how you visualize a neural network. So in neural network, when you have to explain how you went about building a convolutional neural network to classify cats and dogs, you actually have multiple layers that are assembled together. So there is a convolutional layer, then there is an activation function, and then you have additional layers, then there is a dense layer, and finally you apply another activation function, and then there is an output layer, and you apply another activation function, and you finally get the results. So that is how you basically explain how your convolutional neural network looks. Now ONNX is very closely mapped to a similar structure. So here you have the computation nodes. Now each node is completely self-sustained or self-contained, and what it basically defines is an operator, and this operator is mapped to the deep learning conventions, and we'll take a closer look at that. So basically a computation node belongs to a graph, and within the computation node you have an input, for example a tensor that is acting as an input to the computation node. Then there's an operator. The operator is where the actual essence of the node lies. It actually performs the actual computation, and then there are some parameters sent to the operator itself, and once the operator gets the input and the parameters, it computes and then it emits the output, which is fed to the next computation node. So that is how a graph is structured. And when we take a closer look at the data types, again, as I said, ONNX is not a black box. It is well documented, and you can actually read through the entire graph structure. So every computation node accepts some inputs and emits one or more output. So in that form, the input could be a tensor type composed of int8, int16, bool, float16, and all of them. So these are the standard data types that are supported by the computational nodes inside a graph. And this is how you basically do a forward propagation when you're performing inference. So a tensor could be composed of any of these data types, and it could become the input to one of the computational nodes. An operator performs the actual computation and spits out the output, again, which is a tensor, and that goes as an input into the next computation node. Because the traditional machine learning doesn't have tensors and the graph structure in a typical neural network form, there are only two non-tensor types, sequence and map. So obviously we don't use tensors in scikit-learn. You actually have sequence and map as some of the types that are available in ONNX ML, which is the traditional classical machine learning format. Operators are very, very essential. So an operator basically maps the ONNX operator type with the higher level framework or the toolkit. For example, when you're converting a TensorFlow model to ONNX, and you can actually read your TensorFlow model, for example, by opening that in TensorBoard and by looking at your entire graph. So each of the nodes in your TensorFlow graph will be mapped to the same set of operators that are aligned and associated with ONNX. So if you are interested in understanding these operators, it's a part of the spec. And if you actually see my screen, you notice that there are up to 128 operators defined as a part of AI.ONNX. And for example, if you are building a convolutional neural network, you will have, for example, ReLU as one of the activation function. So ReLU shows up as an operator, and it accepts a tensor as an input and sends out another tensor as an output. And similarly, you may actually have, for example, sigmoid is another popular activation function. So this is sigmoid operator. Similarly, you have tanh, all the popular activation functions and the convolutional operations that you perform, all of them are available as ONNX operators. And as we can see, all of them can be very quickly mapped to their counterparts defined in TensorFlow or PyTorch. So essentially, you can interpret the model and do a one-on-one mapping between your high-level a graph structure defined in your favorite framework or toolkit to the actual operator that is available within ONNX. So that's about core ops operators. You can also define custom operators. For example, if you actually go to an advanced level where you are defining your own activation function, or you are creating a new technique that is not mapped to one of the available ONNX operators, you can even define a custom operator. And this custom operator will be used when you're exporting a model that is using a custom operator at your framework level into ONNX. So these operators are essentially mapped to some of the popular problem areas like image classification, which deals with convolutional neural networks, and then the recommendation services that you actually build, natural language processing, and even time series, LSTM-like models that you actually build in high-level languages, high-level frameworks. All of them can be mapped to the ONNX operators. So we'll take a closer look at this. By looking at the very first, the hello world equivalent of an ONNX. So the very first demo that I want to show you is extremely simple, but this is just to get familiar with the way we deal with ONNX. So I have a very simple Python virtual environment defined here, running scikit-learn, the ONNX framework, then a conversion module, a library called scikit-learn to ONNX, of course joblib, which will persist my model, serialize my model, and ONNX runtime. We haven't touched ONNX runtime, but I'm actually using it in my demo. I'll come to this right after the demo. So let's take a look at my train.py. So it is a pretty straightforward, hardly 10 lines of code. It basically takes the iris data set, applies the random forest classifier, and then does a fit and dumps the classifier as a pickle file into the output directory. So let me remove whatever we have in output directory. So when I actually run this, nothing fancy. For the first time I run, it's going to take a while, but looks like it's already loaded. So, within the output, you'll actually see model.pickle file. So this is, let's say, our sklearn model. Now I can actually give you the pickle file, and you can install sklearn and joblib, load the pickle file, and then deserialize the classifier and use it for inference. But can we convert that to ONNX and make it more portable? So of course, this is a very, very simple, trivial program or a model. You really don't need to export and import. But in terms of workflow, now that we have our fully trained model, let's actually convert this. And to convert, we use a framework specific converter, and this is the point that I want to drive across. So just like you have SKL to ONNX, there is an ONNX TF, ONNX for PyTorch, and ONNX for Cafe, Chainer, and so on. So this is where you basically deal with the converter. So here we load from a pre-trained model, that is model.pickle, and then we basically convert the data type, and we convert the pickle file into an ONNX format and write it to the model.onnx file. Pretty straightforward, just about 6-7 lines of code. So let me run this. So Python convert.py, and this will okay, it is there is a file called model.pickle. Why is it not opening? Okay, it is actually mode.pickle. There was a typo. Let me continue the typo. So so we'll convert this, and then when we actually convert the file, we have model.onnx. And how do we take a look at this? Well, the demo is all about exploring the model. So let me go to the output directory and simply open the model.onnx file. So when we open the model.onnx file, I'm actually using a tool called Netron. So Netron is another open source tool that is a part of the ONNX ecosystem, and we can actually use this to understand the actual structure of our model. So pretty simple, but what I want to drive here is the idea that the ONNX model is a very interpretable, transparent format that you can actually parse. You can even export the ONNX file to a protobuf and open the protobuf programmatically and iterate over the nodes that are available inside the model. So in this case, because we are not using a deep learning neural network, we are actually using float input, which is going to take an array and then use the tree ensemble classifier operator. And it is going to basically cast it to the output label, and we use zip map to basically come out with the output probability, which will assign the output to one of the labels defined here. So once we have this model, I can actually perform inferencing. So how will the code for inferencing look like? Well, here is my test data set. So I have a NumPy array with 3 elements. So this is the iris data set, and each of these elements actually represents a different class of the iris flower. So how do we perform inferencing? Well, just open the file and create a session. So when you say runtime.inference session and point it to a model.onnx file, we are creating a session. And then we grab the input name, and this input name is coming from this. So float input is the input name. So we programmatically grab the input name, and we also get the label name if it is associated. And then here I don't have the strings. Basically, the classifier uses 0, 1, 2, 3, and so on. So don't expect the flower name. It's been already one hot encoded, and it is actually using the index rather than the actual string. So then we basically use session.run to send the label name that is already pre-populated, and then we pass the float32 NumPy array. We cast it into float32 just to make sure that it is aligned with the input here. So I'm not sure if this is visible. Unfortunately, I can't increase the font size of this, but if you actually see, this is accepting float32 as the input. So I can even check out what is the node name and what is the input data type. So it basically accepts a float32 array with 4 elements, and that's exactly what we are passing here. So we pass that, and then we print the prediction, and prediction comes back with another NumPy array. And because we are feeding in 3 different elements, we'll get the classification for all the 3. So let's go ahead and run this. Again, nothing fancy. I just want to show you how this pipeline works like. So when I run infer 0 to 1, each of those numbers represent one of the labels associated with the iris data set. So that's how you basically take an existing model, or you train a model and then convert it using an appropriate conversion library, and explore the model by opening that in Netron or programmatically reading that through a protobuf library, and then using it for inferencing. Now, the beauty is when we are actually inferencing, there is absolutely no reference to sklearn, and we don't really need to. So the idea is we are now completely decoupled from sklearn. So as long as you have the ONNX runtime, you don't need to worry about where the model has come from. That is the beauty of it. And if you are actually familiar with Microsoft COM or JVM, if you actually get a jar file, or if you get a DLL file, you don't need to worry about whether it was written in C++ or C# or VB.NET before you consume. As long as you are able to inspect the DLL or the jar file and know what methods to call on that, you can consume it. Now, ONNX is very similar. So you take the actual file, fully trained model, run it through the converter, bring it to an IR. IR is the intermediate representation. And once the model is converted to IR, you don't need to know about the source, but it is actually available as a part of the framework. So if you look at the model here, when I select this, it actually tells me again, sorry about this, the font is too small, but it actually tells us that this has been trained by scikit-learn and it was used by a scale to ONNX 1.7 version of the library to convert. It also tells us what to expect as input and what to expect as output. So all of that is well defined within the spec, and the ONNX file is just a container, a logical boundary for this. Excellent. So that was the first demo, almost like the hello world of ONNX. Now let's move to ONNX Runtime. So now we have seen how ONNX file format and the operators are defined. So if you have to define ONNX in one line, it is a portable, independent format to define a model's graph and models operators in an extremely well-defined specification. So that's all is ONNX. So, and ONNX deals with just two things: the file format and the graph that is inside the file format. Those are the only two things that the ONNX spec actually defines. And you can go ahead and explore this on GitHub. So here, I'm currently looking at the ONNX spec. So this is the ir.md, which will talk about how the intermediate representation is laid out. It is runtime agnostic. There is versioning scheme, and this is the model spec, how the actual model is defined. And within the model, you have operators, operator sets, and operator sets contain operators, and multiple such operators form the graph, and abstracting the operator is the computation node. So all of that is very well defined. So that is ONNX. Now ONNX Runtime is very different. It's very different in the sense from a organizational open source governance perspective. ONNX Runtime was created by Microsoft. Of course, ONNX was also created, or rather contributed from Microsoft, but ONNX Runtime was exclusively developed at Microsoft, but eventually became an open source project. And the key distinction between ONNX and ONNX Runtime is ONNX is a part of Linux Foundation LFAI, and ONNX Runtime is just an open source project under MIT license. It is not a part of LFAI yet, and Microsoft is the biggest proponent of ONNX Runtime. Others are coming on board, but this is a project driven, owned, championed, and advocated by Microsoft. This is technically a different project from ONNX. That is very important to understand. And of course, it actually takes ONNX promise to the next level by creating the actual runtime. So again, if you come from the Microsoft side of world, think of ONNX Runtime as the common language runtime, and ONNX as the CLI and the IR, the common language interface, and the MSIL, which was a part of the intermediate language. Those two are very different. And ONNX Runtime is exactly like common language runtime. So they can exist independently. But ONNX Runtime takes advantage of the ONNX spec to parse and perform runtime inference and also training. And Microsoft is betting big on ONNX Runtime. It is a part of Windows WinML, which is bundled with Windows 10, and you can actually see this in Windows 10. It is becoming the de facto layer for WinML. So this is the best way to visualize ONNX Runtime and the relationship between ONNX and ONNX Runtime. So the topmost layer represents the set of frameworks and toolkits we deal with. And all of them can talk to ONNX through their respective converters. For example, ONNX to TF, sklearn to ONNX, All of those basically define the import and export capability from their respective environments into ONNX. And then this model, the ONNX model, can be fed to an ONNX runtime. And the biggest promise of ONNX runtime is it abstracts away the underlying hardware. For example, if you're dealing with Intel CPU and you want to use OpenVINO, you're dealing with NVIDIA GPU and you want to use TensorRT, you are using Intel FPGA and one API or one DNN, and again you are using Movidius and Mirai, and you want to optimize it with OpenVINO or any other third-party ASIC like the Qualcomm GPU or X-Links. It doesn't really matter. So ONNX uses a concept called execution provider, that is a plugin model. So tomorrow you want to bring a third-party ASIC that is currently not supported by ONNX. All that you as the hardware vendor got to do is basically build an execution provider. So this execution provider will interface with your existing drivers and libraries and exposes the common syntax, semantics, and the conventions to ONNX runtime. So the combination of ONNX file format and the spec with ONNX runtime defines the future of portable deep learning models. This is extremely powerful, and Microsoft has published many benchmarks, and they have proven multiple times that ONNX runtime is highly performant, and a lot of product teams within Microsoft are basically adopting ONNX runtime as their preferred de facto deep learning runtime. From Bing to Microsoft Cognitive Services to a lot of other products, including Office 365. A lot of AI infusion at Microsoft is based on ONNX runtime. So that is the big picture on how things pan out, all the way from your favorite framework toolkit to the underlying training and inference hardware. So how do you get ONNX models that you can run on top of ONNX runtime? There are 4 ways. The first one is there is something called a Model Zoo. You can go to github.com/ONNX and go to models. There are more than a dozen models that are pre-trained, and all of them are available as .ONNX files from MobileNet, ResNet, SqueezeNet, LXNet, CafeNet. This is just a subset. Similarly, for speech processing and NLP, you have everything from BERT models to WaveNet and so on. So ONNX is not just confined to computer vision or NLP or time series modeling or recommendation service. It is basically spanning the entire spectrum, and you have pre-trained models that you can directly consume. This is the first and the easiest mechanism. The second one is to use Microsoft's Azure Custom Vision. In fact, I'm going to do a webinar very soon on this, where we use AutoML, which is Microsoft's Custom Vision cognitive service. We upload a bunch of photos. For example, we'll upload 100 images with people wearing masks and 100 images without masks, and we will train the model. And now the model can basically classify a face with a mask and without a mask. And then we can download the outcome, the model, the fully trained model as an ONNX model, and then run it on top of ONNX runtime. Very straightforward. And you don't need to worry about TensorFlow versus PyTorch versus any of that, because the model comes out with an ONNX format, ready to be executed on an ONNX runtime. That is the second technique. The third technique is what we have done in the Hello World demo. Basically take an existing model and convert it. And all of these formats are supported, from Keras to TensorFlow to Core ML to ML.NET, mix and match. You take a model from PyTorch, consume it in TensorFlow, which is actually my next demo. So you can do all of that. And the third one, actually the fourth one, the last one is use Azure ML to train the model and deploy it either in the cloud or at the edge. So if you have been attending my webinars, I have done a bunch of webinars on Azure ML. So you can basically train, then register the model, create a scoring file, and create the compute which is responsible for hosting the model within the cloud. For example, Azure Kubernetes or Data Science VM or an ACI if you are using a dev test environment, Azure Container Instance, or you could also push it to the IoT edge device to run on Jetson Nano or a Raspberry Pi or Jetson Xavier. So those are the 4 techniques. We have already seen, which is Netron. So this is actually a graph as visualized by Netron. So Netron reads the ONNX format and lays out a very nice visual graph. This is one of the projects that is closely associated with ONNX. Similarly, Beidou, the company that the Chinese company that created Paddle framework, has created Visual DL that not only visualizes and parses the Paddle framework, but also ONNX. So you can use any of these tools. So let's now use one of the techniques that I described, which is downloading a model from the Model Zoo and using it for inference. And this is our introduction to ONNX Runtime. So let me deactivate this virtual environment and go to my second demo. Okay, so here the workflow is pretty straightforward. We're going to grab an existing ONNX model and perform inferencing. Again, nothing fancy. So this is the URL from where I get the pre-trained MNIST ONNX model. This is coming from the Model Zoo, and this was trained using CNTK, Microsoft's cognitive toolkit. So once we have this file, we can untar it, and it goes into the MNIST directory, and you see there is a model.onnx. So this model.onnx represents the ONNX version of the popular MNIST model. So I have some test images. This represents 7. I have another test image which shows 5. So these are the test images that we're going to use for inferencing. So once we have the inference, the model, how do we perform inference? Pretty straightforward. So if you actually look at my requirements.txt for pip, it uses ONNX, ONNX Runtime, NumPy, and OpenCV. Those are the libraries. And let me show you infer.py. 30 lines of code, pretty straightforward. We basically open model.onnx and we pass a parameter, which is one of the handwritten images. Here we pre-process the image. We first load the handwritten MNIST image into OpenCV. Then we convert that into grayscale. This line basically converts the image into grayscale in case it is not. Even otherwise, it is basically the output is a grayscale image, and then we resize it appropriately to make sure that we use the exact dimensions and the shape, which is 1 channel 28 by 28 tensor. So we do that with the pre-processing, and then we convert this into a list with the label as data. This is basically a dictionary, and then we use the NumPy array to convert this input into float 32, and we pass the data type to actual session. So here you see the no, we're actually setting up the session. So we are simply opening up the model, which is model.onnx. Then we grab the input, we grab the output node, and then when we do a session.run, we are sending in the data that is a pre-populated tensor with actual input image, resized and pre-processed. And then we get back the prediction and we print the prediction. We use the argmax to filter out and print the actual value of the prediction. Pretty straightforward. And this is how you actually infer any MNIST image. So let's go ahead and run this. So okay, I need to send the image name. So here it actually prints the name of the input node and the name of the output node and the actual value. So if you open 0.png, this is actually a digit 7. So it is accurate. Now, if I send 5.png, it predicts 5. So the model is pretty accurate. So that is how you deal with the inference. Downloading a model from the Model Zoo. And now we can even open model.onnx, and model.onnx will look something like this. So let me go ahead and zooming in with Netron is still a big challenge, and I have a pretty large monitor, so bear with me while I get this right. This is the max that I can go to, and if you actually notice, this is the input node, and it goes through a convolution. Then there is a ReLU, there is max pool. This is a very simple convolutional neural network, and basically the input accepts a float 32 array or a tensor with the actual MNIST dimensions, which is 28 by 28 and one channel, and then it comes out with another float 32, any value between 1 to 10. So that's how you basically visualize the graphic. So here you also notice that it is originally developed in CNTK and used ONNX converter to convert the file from from CNTK to ONNX. So that was a quick demo of the actual inference by downloading one of the files from the Model Zoo. The last demo that I want to show you, which is actually more realistic and slightly complex, is this. So we have a PyTorch a training program, and when we train the model, it comes out as a PyTorch model. We run it through ONNX, and we convert the ONNX model into a protobuf file that can be directly used in TensorFlow. So this is a very real world use case where we train in PyTorch but perform the inference in TensorFlow. So let's actually use the demo. So this is like the end-to-end demo where we use training, we use conversion, and then perform the final inference. So let's go ahead and do that. So I'm going to deactivate this environment and switch to my demo 3 folder and set the virtual environment. All right. So let me get rid of some unwanted things like the original Netron that I showed, and then close my editor. And I want to show you train.py. This is basically the PyTorch code, again, to train MNIST. I don't want to overwhelm you with large data set and a pretty complex CNN, but this is a very straightforward code to basically train MNIST in PyTorch. So we have a class that is the neural network, and we define the graph here. It has a bunch of activation functions and layers like max pool and so on. And then we perform train, and once the training is done, it basically writes the output to model.pt. And since this actually takes a while on CPU, I'm going to skip running the train program. It is just like I need to run it at least 3 epochs 3 times to get the model. Now hopefully my model is still available. There it is. So model.pt is what actually came out from the training process for this PyTorch program, right? So we have the PyTorch model, and now we need to convert that into TensorFlow. No, actually first into ONNX. So my next step in the pipeline is convert the model.pt into model.ONNX. So what do? We basically repeat the same neural network structure because this is important. This actually defines the baseline network. And once we have this neural network, we load the PyTorch model using this function that says load state dictionary, and then we basically export the PyTorch model into an ONNX model. So again, very straightforward. And if you notice, we are actually not using any specific library for conversion. That's because PyTorch comes with an inbuilt export tool for PyTorch to ONNX. So we have this in place. So now I'm going to run the convert.py, which will basically take our PyTorch model and converts that into an ONNX model. So this is going to take a few seconds, and then in the output we'll actually find an ONNX file, model.onnx, and we can also open that in Netron. Okay, so here comes Netron again. I don't want to fiddle with it, but you actually see it is a straight representation of the net that we defined here. The net class can be actually mapped to each of these layers. There is a convolutional layer, then there is a ReLU, then there is max pooling. You know, basically this is the TensorFlow. This is, I'm sorry, this is the ONNX representation, and this is the PyTorch representation, and there is a one-on-one mapping between these two. All right, so now we have done 2 steps in the pipeline. Train the model, convert that to ONNX. Then the next step is to convert it into TensorFlow. So here, again, just 3 lines of code. So I import ONNX, and from ONNX tf.backend import prepare. We load the ONNX model. We call prepare. It can't get simpler than this. And we write the output into model.pb. And this pb is the saved model format of TensorFlow. So I'm going to run ONNX to TensorFlow. And what this basically does is it's going to throw a bunch of warnings and deprecation warnings, but don't worry about it. Now, this will result in a PB file, which is the TensorFlow protobuf, which is the saved model version. And by the way, we can also open this in Netron. So Netron output model.pb. So, oh, okay, I can't use Netron. I need to use open, which is associated. And this is the TensorFlow representation of the same model, and it is extremely big, and it is actually much complicated than what we have seen with PyTorch. That's because there is a lot of mapping that has gone into PyTorch to ONNX, ONNX to protobuf. But we don't need to worry. Finally, when we actually perform inference, so let me open infer.py. And again, this is very similar to the previous inference. Here, what I want to show you is I have nothing to do with ONNX. For inferencing, I am in the native TensorFlow world. There is no reference to ONNX. I'm actually reading the saved model protobuf. I'm performing the pre-processing and generating the graph, and basically getting the input tensor name and the output tensor name. And I had to hard code this. There are ways to get this programmatically, but I have hard coded it based on the Netron output. And then we finally run the session.run with the input tensor, and it comes back, and we apply an argmax, and we print the prediction. Again, very straightforward, but no reference to ONNX whatsoever. So let's go ahead and run this. And by the way, this will not work with TensorFlow 2.x. So if you look at my requirements.txt, this works only with the older versions of TensorFlow 1.x, and the latest 1.x that you can use safely is 1.15. So don't try this with 1.2, or I'm sorry, 2.0 or 2.0 plus. It doesn't work. So now let's go ahead and do an infer. So when we run infer, it's going to take a little longer. Oh, not, I actually cached it. Okay, so it is printing 7 because we are using 0.png. Now let me change this to 5.png and run the infer again, and it should print 5. Okay, I don't think I have, okay, I don't have the 5.png here. Never mind, you get the point. It is basically, inferencing on the input. So that is how we have gone through the complete pipeline from PyTorch to ONNX to TensorFlow, and finally performing inference. So that brings us to the end of the session. We are almost out of time. And if you are really interested, I am running a series on ONNX at the new stack. One of my first articles should have gone live by now. For the next 4 weeks, you'll actually see a lot of discussion and tutorials exactly on each of the demos that I have shown you. All of the source code all of the scripts will be available at the new stack. So I want to thank our sponsors, Google Cloud, for supporting me with the infrastructure and all the resources, New Stack, my media partner, Foghorn, one of my clients, an edge computing company in Sunnyvale, Portworx, one of the sponsors and also my client based out of Bay Area, a container native storage company. I want to thank them for their support. And that brings us to the end of this session. Very soon, I'll upload the video to my site, janakiram.com/webinars, and you can find the recorded video in a couple of days. Thanks again for attending. And if you are around and if you have patience, I want to bring up a quick poll. Please take a second to respond to this. How relevant was the webinar for you? Great. Okay, so that is very encouraging. And one final poll before you drop off. How do you rate the overall experience of attending this webinar? From the audio, visual to the content, my slides, the demos, my presentation. This is basically the overall rating that you would want to give. All right, that's very encouraging. Thank you so much. Most of you felt it was good and excellent, very encouraging. Thank you, and I'm going to come back to you with another session on Microsoft's distributed application runtime called Dapper in my modern infrastructure track next month. I'm actually pushing my Dapper session from next week to next month because of some uncontrollable reasons. So I'll see you in my next webinar. Thanks again. Stay safe. Take care of yourself, and I will see you in my next webinar in August. Thank you.